Hi, I'm Titus. I'm the head coder for 27545, and I'm going to be going over the simple math and terminology behind our drive2 function with odometry. And we're going to be just taking you through some of the basics so you can get started doing your own research. In the description, you will find a few videos that will be really helpful for mecanum wheels and PID controllers, as well as a GitHub repo with a drivetrain class that you can get started with your own odometry and drive functions today. It should be super simple to set up. All you got to do is quickly tune your PID controller, of course, have your wheel orientation correct, and you should be able to use odometry getting started. Our odometry is based on your starting position, and all it does is take you from your target or your position to a target position in target heading. So let's talk about the simple idea behind it here. The easiest way to get to that point, or the first way you'd probably think of, is to drive forward along your y-axis here, and then drive to the side along your x-axis. We use GoBuilda odometry pods. You can use any odometry pods, but you might have to modify your code if you're not using GoBuilda pods here. I say that because GoBuilda, they reversed it, and this is the x, and this is the y for some reason. Anyways, but of course, the problem with this is you're going along a right angle here, and so you're going to lose all your momentum. So an easier way would, of course, be to just go along the hypotenuse. You can see here it's just the most direct path from point 1 to point 2. So we already know the amount we need to go forward and the amount we need to go x. We just want to go at them at the same time. So to do that, first calculate your velocity x and your velocity y, because the distances won't obviously work directly as your speeds. We're gonna need proportionally make them slow them down, and of course make sure they're between a maximum and minimum. So the velocity x will be minimum. The velocity x will be greater than the minimum, and your velocity x will be the distance x, so x, and it's going to be multiplied by a proportional constant, and that's just going to turn it into wheel motor power. So if x is 3, at distance 3 we want it to be going at 0.5 speed, and so if you took 3, you divided it by if you took your target velocity, 0.5 speed, divided that by the distance distance away you want to be at that speed, then you could find your proportional constant. Do be careful of overshoot though. We don't have a derivative controller in here, which would be the opposite of it would counteract your velocity, so it'd make sure you don't overshoot. So you're probably gonna need a little bit higher. You're gonna need to slow down sooner, so that way you don't overshoot your target here. Constant, and then of course make sure it's less than the maximum, and then the same thing for velocity y, just with your y value times, again, your proportional constant here. There's a slight problem to this though, is when dealing with your Jacobian matrices here. So we're going to go to this target, and we're going to feed our velocity x and our velocity y to a method that will use the Jacobian matrix for mecanum wheels, and it's going to use some rotational matrices, or a rotational matrix, to find the wheel motor powers to go at the angle, at the velocity you want, the angle and distance you want toward your target. However, the way we do it with our apply mecanum power is that it is relative, so we need to relative to the bot's heading. So we need to account for the bot's heading if we're trying to get to this point right here. But let's say our bot is not straight forward at 0 degrees. If it's at a slight offset, let's say it's at a slight offset where if it goes directly forward relative to its heading, like if it goes exactly this way, it's going to go to its point. And so all we're going to do is we're going to take our velocity x, that's going to be equal to, or your velocity forward now relative to the bot, the forward velocity, is going to be equal to your velocity x times the cosine of your heading plus the velocity y times the sine of your heading, and the velocity for your strafing, so your side to side here, your side to side motion is going to be your negative velocity y times your cosine of your heading plus the velocity x times the sine of your heading. And that's just going to rotate your coordinates, so that way it knows that it can actually go straight forward, in that instead of going this way, because originally if it thinks that its heading is 0, then that would be the direct path toward that. And then you can send that Jacobian matrices, like I said, and that's going to move it toward there. And so that's the basic idea, with some proportional constant, with a proportional constant that's going to slow it down as it gets closer to its point. And Jacobian matrices that are going to tell it at what heading, what motors it needs to fire. In this case, at this direction, I think it could fire, if I have this diagram right, these two motors, versus at this orientation, it can fire all of these motors. So that's the basics of how our method works. If you have any questions, go ahead and leave them in the description, and hopefully we can get to them. Hopefully this is just a easy explanation that you can get through quickly, and you can get started diagnosing problems if you have any. Again, leave your questions in the description. I'm just trying to get through this really quickly so you guys can have an idea of how to get this done.